Good morning, and my apologies. I had an interview and I missed the time. I thought I was at 10:40. But nonetheless, we have some minutes to show you some aspects. And since I believe that most of the people are familiar with the relevance of heat pumps and how heat pumps work, I can more or less skip the first slides. Here, however, you see our portfolio, and we are actually a compressor manufacturer for piston and screw compressors, but we also have the complete packaged solutions, like complete chillers and heat pumps, control solutions, and valves, filter safety devices, and all the service equipment. This is also something I would like to skip because that's what I said. I think you're all familiar with the problem of heat generation, which is mostly based on fossil fuels, and that the decarbonization is extremely urgent and important. And heat pumps are, of course, one of the technologies that can generate heat in a sustainable way. This statistic is interesting because here you see the thermal demand in the European Union. The picture worldwide is quite similar, I would say. And you see that the refrigeration or the cooling need is actually just a very fraction of the big heating load. Yeah? So here's the great potential. If we go to more into processes and temperatures, then we see some example processes, and we see those processes require different temperature levels. Some are in a range which will become difficult to cover with heat pumps. In the range below 100 degrees Celsius, there are a lot of standardized heat pumps now, also on an industrial level. Often, or some of them are running with the natural refrigerants, and especially ammonia. It's not only the completely natural refrigerant, climate neutral, but it's also very, very efficient. Yeah. Here in the higher temperature range, and you also see that at Chillventa, there are a lot of activities with alternative refrigerants, even different compressor technologies. So you have a lot of players now doing a lot of R&D activities in these higher temperature ranges. This is also something I would skip because that's more a bit of an introduction. Of course, there are different technologies. Heat pump is just one of them. But it's extremely efficient. And here I have a little example, and I'm sorry this appears all at the same time, but let me walk you through this. This is an application case where we say if you would like to generate 1 megawatt of heat, a boiler is the opposite choice, and so far it has been the opposite choice, so in 90% of the cases the boiler still is in place. However, with an efficiency of roughly 80%, you would need 1.25 megawatt of primary energy to fuel the boiler to achieve this 1 megawatt heating rating. With the heat pump, however, it very much, of course, depends on the COP. So the COP as the ratio of the heating rating, basically what you get out of it, divided by what you need to put in, that's your COP. So in case of a COP of 5, which is a realistic COP if you're talking about industrial heat pump, that's taking a heat source at a sufficiently high temperature level. So that is a very realistic COP with our heat pumps. This means the electric energy input is only 0.2 megawatt. Why? Because it balances with the help of available heat sources. And so you do the math and you see that the energy consumption of the heat pump is much, much lower, but it's of course very much depending on the COP, and that's why it's so important to make heat pump efficient. If you take that general case and transfer it to a realistic customer case, and this has been a real case from a beverage production. Here's some statistics. Let's not go through them in detail now. You will get a handout so you can read up on that. There are some financials, and actually that's the case done in 21 before the Ukraine crisis and the energy crisis. So this is something that I would say it's even more expensive nowadays. Also electric prices. We calculate with some maintenance cost here yearly. So basically what you see here is there's an investment for a heat pump, and then you have annual servicing costs, and you have, of course, the electricity cost. But as said, compared to the gas price and the gas consumption of boiler, you have a significant energy saving over the heat pumps. And what comes on top is the avoided CO2 taxes, calculated with this value for now, but it will increase in the future. And you also have water savings, because what you do is you're using the, instead of releasing the heat from existing chillers to condensed water, you directly feed that energy, that heating energy, from the chiller to the heat pump. So you're also saving water, you have water savings. So this is a realistic case. And considering the current developments, I would even say it's even more optimistic now. Yeah. Actually, it's more or less one of the final slides. Again, sorry for having this appear all at once, but let's start on the very left-hand side. Or let me go back. This is a case where we would supply heat pumps for moderate temperatures below 100 degrees Celsius. If we go above, then we need to think of alternatives, because ammonia heat pumps, which are so efficient and which get you this economic advantage, it's hard to have ammonia used for even higher temperatures. There are ways, for example, with hybrid heat pumps. So you have this ammonia cycle, and then there's an absorption cycle on top, which makes you reach temperatures, high temperatures, even with ammonia in a very efficient way. But it's quite a complex system, so you have high investment prices. But these hybrid heat pumps exist. You could try and push, even with a regular compression cycle, to push ammonia to higher temperatures. Then you need components for this high pressure stage, which is costly. Yeah? So we expect that a heat pump would be at least, or 50% to twice as more expensive. So one of the alternatives to avoid the high pressure is to look for alternative refrigerants. Yeah? And then there's a lot of talk of butane, pentane, or isobutane, for example. It's manageable in terms of pressure. It's not rocket science, it's easy, but there is less volumetric efficiency in these refrigerants than in natural refrigerants like ammonia. So you have a bit of an efficiency disadvantage against ammonia, but it's manageable, and the investment costs are not going crazy. And thirdly, you have, of course, the whole idea of mechanical vapor compression, and here we also see a lot of activities. And I think one of the next presentations will look into this topic here. Yeah, that's basically in a nutshell of how we can reach temperatures higher than 90, 95, or how we go above 100 degrees Celsius with heat pumps. Sorry for this very short presentation, to the point, and visit our booth for more details, also for more detailed activities and components for heat pumps and also for higher temperatures. And there is another presentation tomorrow on time, I believe. So thank you very much.